Uh, my name is QuanSheng Wu, and thank you very much for the organization. And I'm glad to be here to share our recent work, Chiral Decomposition of the twisted M plus M graphene multilayers with arbitrary stacking. And at the beginning, I would like to thank you, my collaborators, Shen Nan from EPFL and Bo Jianpeng from the Shanghai Tech University, and Oleg from EPFL. After the discovery of the superconductivity and the correlated insulators on twisted bilayer graphene, there are numerous studies on the twisted graphene moire superlattices. And for example, twisted bilayer graphene and the twisted mono and bilayer graphene. They put in bilayer graphene onto a monolayer graphene and make a twist, and also twisted double bilayer graphene. And the band structure looks very similar. There's a very flat bands at the Fermi level and separate from the remote bands. And recently, the people are trying to make more complicated moire superlattice. For example, the twisted trilayer graphene. They make a twist. They twist the middle layer of a trilayer graphene, and the band structures. The band structure is like looks like this. There's a flat band, but consistent, but superposition with a linear direct cone. And there are also other more complicated stacking moire superlattices. For example, the M layers plus M layers bonus stacked graphene. M layer graphene twisted with respect to N layer a bonus stacked graphene, and the band structure is also looks very complicated. It's a flat band. It's a superposition with some other direct states. It's dispersed direct states. And for the twisted M plus M rhombohedral stacking graphene, it's a kind of simpler, and the flat band is separated from the remote bands. A straightforward question is that what is the band structure for M plus M genetic stacked graphene multilayers? And what is our genetic stacking graphene multilayers? It's a kind of mixing of the bonus stacking and the rhombohedral stacking. Here we don't talk about the AA stack because it's not energetically stable. For example, here it's a ABAC or A-ABAC. This is a bonus stacking. This is a rhombohedral stacking. And if you put together, it's like this. And if you look at the band structure, it's also mixed. It's kind of a mixing of the flat band and there's some direct states that mixing with that. So. So we want to ask, can we build an effective model for the low energy states by just looking at the stacking configuration? And to answer this question, we would like to review the band structure of the genetic stacking graphene multilayers. This work is done in 2018 by me and McDonald. And it's found that for the rhombohedral stacking, it's the band structure close to the Fermi level. It depends on the layers. And for the monolayer graphene, it's linear dispersal, but bilayer is quadratic, and trilayer it's cubic. And the effective model is it's easy to obtain the effective model for this direct states, and we will find that the chirality of this direct states is the same of the number of layers, and this is for the rhombohedral stacking multilayers, and for the genetic states, and me and McDonald point out that the low energy band structure of any graphene multilayers consists of a set of independent pseudo doublets. These pseudo doublets come from the rhombohedral stacking graphene multilayers. For example, the ABA trilayer graphene, the band structure is can be regarded as a linear diagram plus a quadratic diagram. And this can be read by a kind of Chiral decomposition rules. For example, you can decompose this A-BA to A plus BA, or for each segment, it's rhombohedral stacking, and the band structure is easy to read from the decomposition rules. And in order to apply these composition rules to the twisted systems, we would like to also review the effect model of a twisted bilayer graphene. Start from the Bistritz-McDonald model, and this model, this is a continuum model. And if we expand this continuum model, this is the Moiré potential. If we expand this Moiré potential to the linear order of the R divided by AM and perform the following basis transformation, we can obtain a wonderful Hamiltonian. This is called the rotated Hamiltonian. And let's look at the rotated Hamiltonian. When U0 equals 0, this U0 is the intra-sublattice hopping, for example, the AA hopping. If we set U0 is 0, and this is also called the Chiral limit. In this Chiral limit, this Hamiltonian is nothing but two Dirac fermions coupled with two opposite effect magnetic field. This magnetic field is induced by the Moiré potential, and it's straightforward to get the lambda levels since it's Dirac fermions, and in this case we can regard the flat bands. The flat bands can be regarded as the lowest lambda level of our Dirac fermions with opposite magnetic field, and their energy is 0. And so in the Chiral limit, the band structure in the magic angle, the band is totally flat, and the eigenfunction is since the lowest lambda level of our Dirac fermion, it's sublattice polarized. So there are two sublattice polarized lowest lambda level eigenfunctions, and it's straightforward to extend the BM model to the M plus and multi-layer graphene. And there are two layers. It's called Moiré-layers. It's very special since they are coupled with the Moiré potential. By doing the same trick as the previous model, we can do the expansion of the Moiré potential and do the basis transformation. It's like this, and this is the first step to get the effect model. The second step is that since we only care about the effect model close to the flat band, close to Fermi level, so we can project the previous Hamiltonian onto a mixed basis. This basis this basis consists of the Dirac states from the layers other than the Moiré-layers, and also the lowest lambda level from the Moiré-layers. This low lambda levels. And by doing such kind of projection, the previous Hamiltonian is quite simple. It's like this. This TS mix is the coupling between the lambda level to the Dirac states. And this Hamiltonian is a stacking sequence dependent actually. And let's take an example of twist mono and tetra layer multilayer graphene as an example to show how the third step to obtain the effect model. And we see this Hamiltonian it's general in the momentum space. We need, if we want to solve that Hamiltonian, we need to focus on the K value and at the Km prime mean value. We want to focus on this one, and the Hamiltonian is written like this. Then by using the loading perturbation serial, it's by doing some math calculation, it's straightforward to get the effect Hamiltonian. The effect Hamiltonian is consists of a 0 matrix plus quadratic doublets. And this zero matrix describes the flat bands, and this doublets describe the other multilayer graphene. And if this is the band structure calculated from the KP model, and the colored lines are the band structure for the twisted multilayers. And if we project the wave function onto the TBG of the Moiré layers and these layers, and we will find that this and we will find that this twisted multilayer graphene can be regarded as a superposition of TBG layers plus a rhombohedral stacked trilayer graphene. And here, a strange thing is that since we know that the effective model for the trilayer graphene it's cube, but however, by superposition with a TBG, then the chirality of the doublet is reduced. It's reduced by 1. Then it's 2. This is very special for this twisted graphene layers. And we can also we also studied the twisted mono and trilayer multilayer graphene, and the effective model at the K value and K prime mini value is like this. This is can be regarded as a flat band plus a linear cone, and this flat band is coming from the twist mono and bilayer graphene, and plus a linear graphene. If you look at this one, and by doing a more rigorous mathematics, and we can obtain the following table. We can obtain the partition rule is like this. The effect model of a twisted of this kind of twisted multi-layer graphene, it's always can be regarded as a flat bands plus the doublets with chirality K. And these flat bands are coming from the twisted layers. This twisted layers is determined like this. And first, we need to focus on the twist layers, and we find the longest segment close to the twist interface. For example, if we look at A, B, A, B, and we do the Chiral decomposition from the graphene multilayers, this can be decomposed as 1 plus 2 or 2 plus 1, right? But if it's just the trilayer graphene, it doesn't matter how do we decompose 1 plus 2 or 2 plus 1. However, if you put this multilayer graphene into a twist configuration, then we need to choose the longest one. So the band structure of this one can be can be read like this. This is monolayer plus a twist double bilayer graphene plus another monolayer graphene. So, and the chirality of these doublets can be obtained from reading this. But exception is this one. If it's a twist bilayer graphene, then the chirality of this segment will be reduced. And this is the main result. And in the end, I would like to mention that the such kind of flat band plus the doublets, there's no gap. There's no gap in the Chiral limit. However, this the energy gap. However, the gap could be open if we applied the electric field or we consider the lattice relaxation. In our paper, we studied the applied electric field. If we apply the electric field, we find that the flat band is separated from the remote band. And usually that separated bands could carry the non-trivial value chain number. Here the phase diagram by adding electric field and the twistor angle. And after the post our paper, just another study studied the lattice relaxation. They found that the lattice relaxation could also separate the flat band with the remote bands, and also carry a very large non-trivial value chain number. Okay, with that, I would like to thank you all and to take the questions.